It's a pleasure to speak about loop integrands in Yang-Mills theory from forward limit.
Thank you. First, let me thank the organizer giving me this opportunity to introduce our recent work. So this talk is based on the work with Nima, Jean, Carolina, and my advisor Song, and recently with Funky. First, let me introduce the Yang-Mills theory. The Yang-Mills theory is described the massless spin-1 particles we call gluon, not like the scalars, except the momentum vector. Now we need a more vector called polarization vector to describe the spin information. So the polarization vector has the constraint like epsilon I dot pi equals 0, and epsilon square is 0. And massless is m square is 0, and the gluon's amplitudes obey the momentum conservations. Here the n is the number of external points, and d is the space-time dimension. A dot b is the usual Lorentz product by the matrix. Eta mu nu. Next, let's introduce the Feynman rules. We use the wavy line to denote the gluon particles propagate, and eta mu nu over p squares, and the gluon interact were 3 points vertices and 4 points vertices. So we do not explicitly to write down the formula here. We are focusing on the color order Yang-Mills endpoint amplitudes. We contract all the external polarization vector into some lots of Feynman diagrams and do the perturbative expansions. So we have a tree level and one loop and the higher loops contributions. Now we focus on the tree amplitudes is just a rational function, and the usually L loop amplitude is integral to some hard special functions. Now, so we focus on the loop integrands. So those integrands are rational functions so it's very simple for us to introduce to study. So the first question is how to get those amplitudes. The usual people will tell you to draw all the possible Feynman diagrams, but we learn from Jack's talk, and the Feynman diagrams grows very fast, and it's hard to us to calculate. So we need to think about a new, more efficient way to calculate these amplitudes. Let's begin with tree level amplitude. So we already know for the n point massless particles, you can form the now n gons, and to describe the Feynman diagrams, draw pictures of the Feynman diagrams. We used Xij to be the kinematics invariant. All the Xij is corresponding to the chord of the n gon. And the number of the Xij we already learned is n times n minus 3 over 2. And also here we need to more Lorentz invariant, such as epsilon dot epsilon, epsilon I dot epsilon j. They all independent. The number is n times n minus 1 over 2. And we need epsilon I dot pj, but you need to solve the momentum conservation. So the number is n times n minus 2. So we add all those invariant, and the number is 2n times n minus 2, which matching the 2n gon when you take all the scaffolding residues. So if you are interested with the scalar scaffolding gluon storage, you can see our recent papers. But here I want to talk about scaffolding pictures. So now our target for the tree level amplitude, which look like, for example, 3 points, is just a polynomial for the epsilon dot p, and 4 points, it can have 3 diagrams contributions. 2 is the usual the exchange diagrams, and 1 is the 4-point vortex. Start at 5 points. Now you can have the for triangulation and one triangle with the quadrados, and other terms you can get by cyclic permutations. So our amplitude look like at tree level is the rational function with all the poles are xij variables, and the numerator is the polynomial of epsilon dot p and xij. So the question is how to calculate those tree level amplitude without using Feynman diagrams. So the key point here is using the factorization, what we call the factorizations. The picture is like once you take at the pole at xij equals zeros, the amplitude factorize into left hand and the right hand sub amplitudes. But here, differ from the scalar story you are familiar with, we need to introduce the is not a product, it's the tensor product now, because we need to replace the epsilon mu to the matrix. So if we already know all the residue for the scattering amplitude, we can use those residue to reconstruct the endpoint amplitude by just summing over without any overlapping terms. But for n 4 points, there is still has a contact term, just is corresponding to the pole at infinity. So we start at 5 points. Here is the 5-point examples. Once we calculate the residue on x13 equals zeros, we found the 5-point amplitude factorized as the left hand is the 3-point amplitude and the right hand is the 4-point amplitude. They glue together with by the matrix eta mu nu, and we know because we already our input is the 3-point and 4-point amplitude, so we can just reconstruct these residues, and we can calculate other residues by similar technique. Here we found there is some overlap terms, so you need to carefully sum over and without double counting. So the one practical method is to just when you sum over new residues, you let the terms appear before to set to 0, for example, like this. Then you sum over all the residues, and this gives you the 5-point amplitudes. Now let's move on the one loop integrants. Here we first is now it has the loop momentum vectors L, and L square is not zeros. So we need a new kinematics to describe this one loop integrants. We can, for example, at 4-point one loop, we can form as the box, and with the inner punctures, we call the xz. And now the new variables we introduce here is the xiz, shorten is the yi. And for examples, we can draw all the possible full triangulation or less triangulation diagrams. For example, here is you can triangulation this box, and we give you the box diagrams, and you have triangle diagrams, and we call the massive bubbles here. And notice here, all the xij is equal to xji. And we have 2 more diagrams called massive bubbles. But here we are seeing is we need to introduce the xij is equal to 0. It seems singular, and the tadpole diagram with the xii called the tadpole variables. But in the general dimensions, so those massive bubble and the tadpole diagrams are just the integral into zeros, which we call the scaleless integral. So physically, the one loop integrand we are interested in is the start from massive bubble n-gon to triangle and up to n-gon. So the question is, now we can just expand all the expressions which has the pole is some yi and some x, and the numerator is a polynomial of epsilon dot l, epsilon dot p, xij, and yi. So still the question is how to calculate those integrand without using Feynman diagrams. But if you are more interested with the perfect, we call the perfect integrand associated with this, with the surface and the scaffolding stories, you can see our recent paper. The key here, we use the technique called the single cut. Just the residue on the yi equals 0 for the one loop integrand, it becomes the n+1 tree amplitudes, but the two adjacent gluon become in the forward limit. In the forward limit, this is the p plus and the p minus is equal to the momentum is the same, and now you need to glue those two legs. For example, you can see the picture like this, but here when you glue in the forward limit, sometimes it will break the gauge invariance. So you need to add we call gauge turns. This Q is the reference momentums. When you sum over all the possible cuts, the full one loop integrands do not depend on the Q. And see the picture, we just cut here, and yi equals 0, it becomes to the n+2 tree amplitudes. A more efficient way to calculate is what we can see. For example, we call the two adjacent particles plus and minus. You have the two kind of tensor structure, epsilon plus dot epsilon minus, epsilon plus the dot A, epsilon minus dot B. Let's calculate them. And you can see from the calculation, and the epsilon plus dot epsilon minus becomes d minus 2, because the second term is cancelled by to 2. And here the second term, it look like will affect the result, but in this paper they have proved once you already expand the tree amplitude into an independent basis, the second term is you can just efficiently ignore them. So the more efficient glue rules we just replace the epsilon plus dot epsilon minus to d minus 2, and those terms becomes a dot b. So you already know all the information of the single cut. You can use the similar way to reconstruct your rational functions. We already use this method to calculate the result up to 7 points at the one loop. For higher loop, for example, at 2 loop, if you are just interested in the physical integrand, just up to scaleless, you can use the same method to calculate to the rest single cut. Here now, once you cut one single cut, it becomes n+2 one loop integrands. So if you already know the result for the one loop integrand, you can use a similar method to reconstruct your two loop integrand. Here we use the same method to calculate up to 5 points. Sorry, here I just want to quickly review the one loop structure. We already introduced the method to calculate those rational function, but sometimes it look very ugly. So you may wondering, does there has any structure here? Luckily, at one loop, we do have some nice structures, because from the tree amplitude, there is called universal expansions. I will not tell the details, but so I just want to show the formula. So if you are introduced the Young-Mills amplitudes, and you can expand like this. And also, if you replace the two leg by two fermions, this has the same universal expansion, just replace the coefficients to this. And so use the forward limit, you can replace those terms to some trees we defined, and you can also to calculate to combine the two to amplitude at the one loop to give you the more general gauge theory at one loop integrand. So let's start summary. So we just want to use some residual calculation to reconstruct the rational functions. At tree levels, we use factorizations. At loop levels, we think we can use the single cut to reconstruct. And we also found some one loop structures, which can gives us from pure Yang-Mills to get the more general gauge gauge series for especially for super Yang-Mills. Thank you.
Are there any questions?
Can you uplift your perfect one-loop integrand of gauge theory to a gravitational one, maybe for gravity plus B field plus dilaton?
I think now we cannot, because the perfect integrand we're talking about at one loop, we already have the results, but we do not know how to uplift. I don't know, just maybe because we do not know such as like KLT relation at one loop levels or other, because also the question maybe at tree level, we do not know how to relate to our two-gang formula at tree level to flow string at the gravity amplitudes at tree level. So I think we do not know how to apply. Yes.
Okay, good point. I agree that tree level is the first place to look. Yeah.
Yeah.
Okay, thank you.
Yeah.
When you say general gauge theory, you mean you can do some like effective field theory or with derivative interactions, or
No, we just say we can add the what you want you can choose a number of the gluon and the number of the fermion, and also you can add some scalar and into the loop, just one loop. But all the endpoint, external point is still are gluons. So it's not if some effect is zero.
Thanks. Any more questions? If not, thank you.
Thank you.